So in the last class, what we discussed, the disadvantages and advantages of power electronic circuits, and what are the importance of power electronics, what are the inputs required for power electronics, where we can apply for the power electronics. This is just last class what we discussed. And in the last class, I raised one question for you. What is the single statement of the power electronics? What I told? It's a switch. The single statement of the power electronics, it is a switch. Now, we are going to talk about how the switching losses in the device, how the conduction losses in the device, how the questions will come in computer examination, like GATE exam, engineering service exam, how the questions they will frame, all these things today we are going to talk in our session. Now, coming to the switch, generally, if you take a power electronic circuit, what are the major components it consisting of? The power electronic circuit majorly consisting of a switch. That switch may be your SCR, diode, triac, IGBT, something. It is a switch. And also, the second one, we have an inductor. The third one, we have a capacitor. What is the duty of the switch? What is the main duty of the switch? It controls the power flow. Whether power has to flow or does not flow, it can control by using switch. The switch is mainly used to control the power flow. Sir, then immediately you have a question. What is the purpose of inductor? What is the purpose of capacitor? So generally you take in your home there is a switch. What the switch will do? If you switch on, what happens? Light will glow. Power is flowing. When switch is off, the light will not glow. Power is not flowing. That is what it is, a simple statement what I told you. And similarly, coming to the inductor and capacitor, whatever the elements, both are dual in nature. They use it to smoothen the power. It controls the power, it smoothens the power. So these two are used for smoothening. What is that? Smoothening of power. What is smoothening, sir? We are trying to reduce the variations in the voltage, variations in the current. It should not be more fluctuations. To reduce the fluctuations in the power supply, we are going to use inductor and capacitor in a power electronic circuit. Are you got it? So for example, if the voltage is here like this, suppose if the voltage is like this, it is swinging like this. Suppose voltage swing like this, swing like this, swing like this. You don't require this type of ripples. If it is a voltage swinging from here to here and here to here, such a swings are not required most of the cases. If it is a voltage swing, this can be smoothened, this can be reduced by using a capacitor. If it is a current swing, it can be reduced by using an inductor. So the main idea of the inductor and capacitor is used to smoothening the power. The main idea of the switch is to control the power flow. Now, coming to the switch, the switch is in on state and off state. Initially, we can talk ideal switch, then we can go for practical switch, then we can go for some problems in the practical switches. See, generally, we are going to denote our power electronic switch is like this. This is P, this is T, we can represent. What is P? It's a pole. What is T? T is a through. Single pole, single through. Single pole, double through. Like that. In electrical terminology, the switches can be operated like that. That's why I told you, it's a pole, it is a through. Single pole, single throw. Like that, if you have a one pole is like this, your switch arrangement is like this. This is a pole, this is C, this is T. What happened? You can place your switches here, you can place your switches here. Double throw, single pole. This is a single pole, it is a double throw. Like that switches we are using. Even in our chopper circuits, in our future we are talking chopper circuits. In the chopper circuit, this type of switch we are using. It is the basic thing. Suppose if the switch is closing like this, it is going to on state. This is going to on state. Similarly, because you see arrow is indicated for closing. Arrow is indicated for closing. Similarly, we have a switches here. And this is pole and through, single through, like this. The switch is opening. It is going to off state. It is going to on state. It is going to off state. Sir, if you take an ideal switch, switch is ideal. Of course, you know very well, your engineers, nowhere in the world ideal equipment, ideal components, ideal switching is not available. It's only theoretical discussion. If the switch is ideal, during the on state, during its on state, what happened to the voltage during on? When switch is on, what happened? What is the voltage across the switch and what is the current? The voltage across the switch is equal to 0. The voltage across the switch is equal to 0. Once it is closed, it acts like a short circuit. Once it is a short circuit, what is the voltage across the short circuit? Is 0. But no electronic device without internal resistance we can't manufacture. But we are talking, it is an ideal diode, ideal device, ideal SCR. Internal resistance is neglected. That's why voltage drop is 0. Then, what is the current here? Once if the switch is closed, what is the current? Current is greater than minus infinite, in between plus infinite. Lot of current. We don't know, some magnitude will be there. It is greater than, minus infinite, less than, before switch is operating. So it has a infinite current. Current is infinite, simply, and voltage is 0. Then what is the power losses, sir? What is the power losses? We know very well, power is nothing but V into I. One factor is available, other factor is 0, power losses are 0. So, for the ideal case, operation of the switch, energy is not required. The energy losses in the switching for on or off, energy losses are 0, power losses are 0. Similarly, when you are going for off switch, off switch means how this acts like? It acts like an open circuit. In open circuit, sir, why the open circuit, what is the current I? I is equal to 0. Then voltage V is equal to infinite. Then what is the power losses here? The power losses is 0. What is the energy required to turn off your device? Is not required. Energy losses is also 0. But this is only the ideal discussion. Power losses are ideal discussion. Sir, if it is a switching characteristics, if you want to see how these characteristics will appear. For example, see all of you, this graphical representation you can see here. Clearly observe, don't sleep while watching the video. Whenever if you want to gain the knowledge, my advice is, while watching the video, you have to maintain the notes. You should write the notes. Just by watching the videos, I don't think you are going to get the knowledge. Parallelly, you have to maintain your notes. Each and everything. At the end of my class, you are very much confident about power electronics. Oh, power electronics is this much easier. You may feel like that. I am guarantee about that. Now, this is what I can say. This is the voltage V. This is the current I. Current I. For example, if the device is an on state, what is the current magnitude is maximum? The current magnitude is maximum. This is on state. During this interval, what is your voltage magnitude is 0. Here to here voltage is 0. Once if the device is turned off, the current goes to 0 like this. But immediately voltage will rise like this. Voltage will be rises like this. So this is the voltage waveform. This is the current waveform. Again, what happens if you want to turn on the switch? You can have like this. So this is the period. This is the period of on state period. Here to here. This is the off state period. And again, what happened? We told that already. We know that in off state voltage is maximum, current is 0. In on state current is maximum, and voltage is 0. This is what we have. Do you get this type of response? Do you expect this type of response? It is impossible what I can say. Because current cannot change suddenly like this. Voltage cannot be changed suddenly like this. It takes some time to operate. Even you take your switch here, just you can operate switch like this. It takes some time lag. With the 0 time, can you operate the switch? Whether it is a turn on, turn off, not possible. Like that switch also, your power electronics switch will be takes place like here. Are you got it? Now this is about the ideal switch. Then what is the practical switch? What is the practical switch? So coming to the practical switch, it will take some time. It will take some time during the switching operation. Sir, how the time will take here? How the time will take place here? For example, if you see, we have the waveform is like this. We have the waveform. On the same diagram, I am representing both current and voltage. Up to this instant of voltage, for example, this instant of voltage, nothing is operated. I can say it is a 0 time. So already it has some voltage of V volts up to this one, V volts, and the current is 0. Now what I am making here? I am turning on the switch. The switch is trying to turning on. When the switch is turned on means what happened? Current gradually increases. So the current is gradually increases like this. Once if the current is increases, your switch is closing, voltage automatically reduce. This voltage is reduced like this. Because if you see observation, this is called a transition period. You see how the transition period, suddenly it is like this, it is like this. It is impossible. During this on state, we have a losses, energy losses. Those losses are called on state losses. What is that? Switching on state losses. These are called switching on state losses. So sometimes if you see, you are going to take the product. Power loss means what? V into I. This is your voltage, this is current I. Once if the device is on current maximum, voltage becomes 0. This is on state. So this period is called, I can say it is 0. This one we can say as T on like this. So what is the energy losses here? How to calculate the energy losses? For example, if you see here, I can draw this one like this. If you observe very carefully. What is the losses at this instant? Power losses at this instant? Because here current is 0, voltage is maximum, power is 0. Here how this one? Current is maximum, voltage is 0. Then what happened? Power is 0 here. But what happened? Current is slightly increases, power is slightly decreases. At this point, current and voltages are reasonable. So that if you draw the graph for this one, you can see the energy losses is like this. These are called power losses. This is the power loss curve in the case of, even you take suppose 1 into 9, 2 into something, you multiply, you will get this type of curve. Similarly, when you are coming from the turned off, your device is doing turning off. For example, I am continuing on the same figure, but this is the explanation for what? turn on process, turn on, not process, turn on. During this turn on, how the current is increasing, how the voltage decreasing, how the energy losses will take place. Now, coming to the other one. So the next one, what I am going to do here is, now we are going to turn off the device. Turn off the device. Once turning off, what happened? Voltage will increases. In off state, voltage is maximum, current is 0. So your current will be falling like this. Your current will be falling like this. This current will be falling like this. And your voltage will be rising like this. Magnitudes may be different. It should not be same. Magnitude may be different. It may be different. This is the time period. This period is called, what is this period is called? During this period to this period, this is the turn off time. This is T off. So once if it is off, the voltage is maximum, current is 0. Once it is on, current is maximum, voltage is 0. Like this we can represent. Of course, energy loss, if you calculate for the turn off also, you can get same thing. If you want to calculate the total energy losses is equal to energy losses during on state plus energy losses during off state will give the total switching losses. We can call this one is called blocking losses also. This is called blocking losses also. These are called turn on losses. This is called blocking losses because during blocking we have a losses for this one. This is how a practical switch, whatever we discussed, it is a practical switch. This is the characteristics for ideal switch. This is the characteristics for a practical switch. Is it clear? I think you are clear. In the case of practical switch, it requires some energy. Why, sir? Why? Because the switches also require some energy. For example, my switch is there. Hello, switch open. Hello, switch close. It will close open. We have to do manually, open or close. Some power we have to give. For that, some energy is required. Energy losses will be there. So to turn on the device, a circuit is required. For example, you have a one switch. The switch is to be on. One circuit is required. What that circuit name is called? That circuit name is called as a triggering circuit. A fellow is sleeping. I want to initiate. I want to give some trigger. The circuit is sleeping. You want to make the circuit is on. We have to give some trigger. That's why it is called triggering circuit. And this is also called as the firing circuit. Firing circuit. Don't feel that firing means fire. It is not like that. Fire means you are initiating the circuit or triggering the circuit. Triggering circuit and firing circuit terminology is same. And gate drive circuit. Gate drive circuit or base drive circuit. These are all driving circuits because your BJT is there. The BJT is to come into on state. We have to drive the BJT base with the help of a base. Your SCR is there. We have to MOSFET is there. You have to give some gate drive to turn on the device. Even for SCR, we have to trigger. Gate triggering is required. These are all the terminologies used for the what is it? To turn on the device. So, what is the circuit name for turn off? What is the circuit name for turn off? Tell me, what is the circuit name for turn off? For turn off, a circuit is used is called a commutation circuit. Commutation circuit. For example, one SCR is here. I want to turn off this SCR. I want to turn off this SCR. A circuit is used to call commutation circuit. One SCR is here. I want to turn on the SCR. Then the circuit is used to call any of this one. Any of this one. Is it clear, all of you? I hope you understand what is the gating circuit. Now, if you want to calculate the energy losses, during E represents energy during on state is equal to integral of 0 to T on. Integral of 0 to T on. And what is this one? VI dt. Vi dt. Because interval between 0 to on period, power you are integrating, we are getting energy losses. These units are in joules. These units are in joules. What is the energy? This is called energy loss. Keep it in mind. This is called energy losses during on state. What is the energy losses during off state? I told you just now we discussed diagram. An on state, off state energy loss will be there. This energy losses can be written as integral of 0 to t off. This is on 0 to t on period, 0 to t off period. T off period. What is this one? Vi dt. So what is the relation between power and energy? You see, I will have a power losses. Power losses is equal to 1 by t. Here the t is not there, you can see here. 1 by t integral of 0 to t. What is that one? Ei dt, energy losses. If you add this one and this one, total power we can get. Total time period you can take here. Then power losses is equal to 1 by t into energy losses. Total energy loss during on and off. Then what is the equation we can write for this one? Power losses is equal to 1 by 2. How to write? The frequency. 1 by 2 you can write as frequency into energy losses. So what is the important observation here? The important observation is this frequency. What is this frequency? It is a switching frequency, FSW. Switching frequency. So power losses are more when the switching frequency is more. Power losses are less, hence when the frequency is less. So that one trade mark is required, one trading is required, trade off is required. We should not go for very high frequency. When you are going for very high frequency, what happens? Losses becomes more. We want to see speed, we want to see the losses. We don't want more losses, we need a high speed. So that moderately we have to choose while selecting the circuit. Hence, this is a very important question. The power losses are directly proportional, depends upon the switching frequency. You see here, I am here. For example, I am static like this. I can stand for 1 hour, 2 hours, something like that. I am not doing any work. But suppose I am moving like this. Step, 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 step. This is frequency. On, off, on, off. Cycle, upper, lower, upper, lower, upper, lower. More fast like this, very fast like this. What happens? If I am walking like this, I can lose my energy. Energy losses are more. If I am static like this, even during period cycle, people cannot walk or something. They simply sit down. Because they are not eating anything. Without eating, if you are doing exercise, you may lose. Isn't it not? Similarly, the frequency is nothing but cycles, movement. When the movement is more, power losses are more. That's what it is, a simple indication to understand. So this is the theory about how the switching losses and all. Now we want to concentrate in the mathematical part of the switching. So this is the switching characteristics of one device. The switching characteristics here, you see from 0, interval of 0. Voltage is maximum, current is 0. So already it is in off state. Now the current increases, it will goes to maximum current, voltage becomes to 0. This is T on, I can say. This period is called on period of time. Similarly, I will continue here. This is for, you see, I can say 0. This is voltage became maximum, current becomes 0. This is current, this is voltage. This period is called T off. So this period is called T on period. This period is called T off period. During this period of on state, during this period of off state, we want to calculate the energy losses. So how to calculate the energy loss? What is the equation for this one? What is the voltage equation for this one? If you want to write the voltage equation, V is equal to your voltage V into 1 minus, it varies with the T. T divided by T on. So how we written this equation? You have to go for your basic mathematics. Y is equal to mx plus c. Or y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. That equation also you have to verify if you want. Y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. This is the equation we have to use. Whenever, if you're already having some value, it is decaying, it is reducing, it is falling, you can follow this equation. Otherwise, how I told you the fundamental thing. Similarly, how can I get the current I is equal to? It starts from 0 to the maximum value. It means I into, with respect to t, it is varying, t divided by t r we have to use. This is for this situation. Similarly, how to write this for this one? Can you tell how can you write this one? I is equal to I into 1 minus t by t of, and what is the voltage? V is equal to V into capital V into, what is that? T by T of. So if I used capital letter there, I can use capital letter here. T on and T on like this. Then what is the energy formula? E is equal to integral of 0 to T on. Voltage into current. V into I into 1 minus T by T on into T by T on. Like this. T by T on. Then what it becomes like? You take Vi is outside. What is the equation you got? T by T on minus T square by T on square. T on square you can have into dt. If you integrate it, what it becomes like? T Vi T square by 2T on minus, what is this one? T cube by 3 T on square. The limits are between 0 to T on. If you substitute this one, what happened? T on square by T on cube by T on square. What this becomes like? Vi into T on square divided by 2T on minus T on cube divided by 2T on square. T on square. Of course, what it becomes like? What this becomes like? So Vi T on square, T on. If you take, this is 3. T on if you take outside, because this T on, this square. T on square, this gets cancelled. Vi T on divided by 1 by 2 minus 1 by 3. What this becomes like? Vi into T on divided by 6. This is the energy losses during this turn-on period. Similarly, if you calculate for turn-on period, same equation, but these equations will interchange. Of course, you can observe this one here and here. This will interchange. Finally, you will get the same results. So, total energy losses E is equal to Vi T on by 6 plus Vi T off by 6. That will give total energy losses. You can check another problem. See here, this is the problem. But if you try to identify the difference in the figures, you have to see both the figures. Because here current starts from 0 to something here. Voltage waveform is like this. Of course, voltage waveform is like this. But coming to the current waveform, what is going to happen? From here to here, it is not like that. It maintains a constant like this. It maintains a constant like this. This period is called T on period. This period is called T on period. This period is called T off period. So what are the equations we have to develop? What are the equations we have to develop for this one? I told you now V is equal to capital V into 1 minus T divided by T on. You can take like this. This one is T on. Total period is on period only, no problem. What about the current I is equal to? I is a constant. Up to this one, I is a constant. Hence, you can take I is like this only. Because in the previous case, the current is rising like this. I into T by T on is considered. Now that situation has not raised. So that is the reason energy E is equal to what happened? Energy E is equal to what happened? Integral of 0 to T on Vi 1 minus T divided by T on into dt. If you take the energy E is equal to Vi, you take outside, integral of 1 means what? T minus T square by 2T on. The limits are from 0 to T on. So what it becomes like? Vi T on minus T on divided by 2. Because what happened here? T on and T on. Square is there, na? That gets cancelled. Then what it becomes like? Vi into T on into 1 minus 1 by 2. Then what it becomes like? Vi T on divided by 2. This is what we are going to get. Similarly, if we calculate for off state also, we can get the same thing. This is energy for on. Energy for off is equal to Vi T on divided by 2. You can get. Please go through it. And this is the energy calculation. Sometimes the examiner will ask the power losses. How can you calculate the power losses? If you know the energy losses, how can you calculate the power losses? Power losses is equal to F into energy. This is what two different switching actions are given. Based on this one, we have some problems in the numericals. Numericals will be there. That we can discuss after this session. Okay? Thank you very much, all of you. Bye. Enjoy and subscribe the video. Inform to your friends. And tomorrow I will give you one beautiful question for you. If you answer that question, you are going to get a surprise gift. You can get some surprise gift. Why I am telling last is because those who are interested candidates, those students only can watch these videos. Those who are not having interest, those who are not serious about their career, they don't watch all these things. Simply they will pass like this. But tomorrow you can enjoy one topic, conduction losses. I will ask you one beautiful question. If anybody answer for that question, I will give you one surprise gift for you. Okay? Bye.